we'll talk about oscillators or improperly built amplifiers. Different types, how to stabilize for thermal drift, microphonics, direct digital synthesizers, a different form of oscillator, and phase lock loops, which is another way to do it, and then some high accuracy oscillators. So without an oscillator, you probably couldn't have a radio, unless it's a crystal detector or something. Well, now they had transmitters before. They had oscillators. Spark gap transmitter just put out a little bit of everything. So essentially, an oscillator is an amplifier with a frequency dependent feedback circuit that has enough phase change to make it a positive feedback. It turns out it's not easy to build a working oscillator, as I've learned. In order to provide long-term oscillation, it has to have a feedback gain slightly higher than 1. If it has too much gain, it won't continue to oscillate. It doesn't have enough, it won't oscillate. And you have to have higher gain to get it started. They're little finicky little things. So a lot of times they'll have a special element in there that has a different gain when it starts than when it actually runs as an oscillator. They used to use little incandescent bulb because of the varying resistance of it. So basically, if it's a sine wave oscillator, like we said, it's an amplifier with a feedback network that is frequency dependent. And that feedback network is what controls the output frequency of it. They tend to be, like I said, very sensitive. They don't have much output power typically. So you need some sort of buffer device to isolate it from the rest of the circuitry. Which of the following are basic components of a sine wave oscillator?
Delta.
What determines the frequency of an LC oscillator? Yeah. Okay, there's more than this, but 3 basic types we're going to talk about. A Colpitts, named after some guy Colpitts. Typically, it's used as a VFO because you can usually vary the frequency. The main thing to remember about a Colpitts is the feedback comes from a capacitive divider. So your tank circuit with an inductor and capacitor, you'll have 2 capacitors and you'll take the feedback off of the center of that capacitor. So you're getting half of that signal. In the case of a Hartley, it's just the opposite. You center tap the inductor and take the feedback at that point. So that's how I always remembered them. Colpitts, because it starts with a C, uses the capacitor, and Hartley uses the other one. And then Pierce uses a crystal as the feedback element, as its frequency dependent element. So what are 3 oscillator circuits used in amateur radio equipment?
Charlie. No.
That's
Good
what?
old Taft, huh?
Taft. In a coal pit's oscillator, positive feedback is supplied through the capacitive divider. Yeah.
Two physically different capacities.
Usually they're the same. And in the case of a VFO, that's why you always had two gangs.
But it's two capacitors,
Right,
but they're turned on the same shaft. So
right, right. Or in modern days, maybe two varactors. I'm not sure.
That's the two BFOs.
So how is positive feedback supplied in a coal pit's oscillator?
Charlie.
Yeah. They couldn't say a tapped capacitor because they don't make those. In a Hartley oscillator, like I said, it's through a tapped coil in the tank circuit. So it's essentially the same circuit, it's just where you get your feedback type. And the Pierce, okay, our feedback is through a quartz crystal. And of course, you have to make sure that you've got the parallel capacitance necessary on that crystal for it to operate at the right frequency.
Which capacitor? The one on the left?
They're not showing it, but there should be a parallel capacitor across the quartz crystal. Which if you look at the data sheet for the crystal, it's going to tell you what capacitance it needs, how many picofarads usually, fairly small typically. If you change it, you can change the frequency. Yeah. And what they used to do was, have a variable capacitor in parallel with it so you could tweak the crystal a bit, but not a lot. How is positive feedback supplied in a Pierce oscillator?
Delta.
Which of the following must be done to ensure that a crystal oscillator provides the frequency specified by the crystal manufacturer?
Bravo.
Okay, you can have thermal drift in an LC oscillator as well as a crystal oscillator. So one of the techniques is to use what are called NPO capacitors. I never found out for sure what that stands for, but they're kind of negative temperature. In other words, they compensate for the capacitive change you would normally have with temperature, so that they stay essentially the same over a wide temperature range. Which of the following components can be used to reduce thermal drift in crystal oscillators?
Alpha.
Maybe alpha?
Yeah, could be.
Anybody know what MPO stands for? Okay, microphonics is apparently another issue where physical vibration can affect the oscillator frequency. I can see whether if it's a quartz Pierce oscillator, that vibration might affect the crystal frequency a little bit or modulate it. If it's got an LC and an inductor, depending on how the inductor's made, it could change the inductance. If it was the tunable capacitor with plates, could affect it. So Mechanical vibrations can have some effect on the frequency of the oscillator. So in order to combat that, if it's a problem, you have to physically isolate it so that you can reduce the vibration. So what is a microphonic? How can an oscillator's microphonic responses be reduced?
Delta.
Okay, direct digital synthesizers, where we use, normally it's a crystal oscillator, and then we have some divider circuits so that you can essentially generate any waveform, any frequency you want by that ratio of the two dividers, one in the output circuit. I think there may be a diagram on the next slide or so, maybe easier to explain. The one advantage is they allow you to have a large frequency range with a single crystal oscillator, a fixed crystal oscillator at some frequency, because they're multiplying it up and then dividing it down, and that ratio allows you to have all those fractional frequencies.
Where did it go?
I don't know, other than, let's see. High stability variable frequency oscillator in a transceiver is one of the uses. It's red because there's a question about it.
Oh,
This is a typical one. It's all in that one little package, and has the whole 9 yards in it, where you have a clock, which is generated by adding an external crystal in this case. And that clock runs into the phase accumulator, which is just a counter. And as it counts up, it's addressing different entries in that programmable, the ROM or the PROM, okay? And each cell in there stores a different numerical value representing an amplitude for the waveform. So as it steps through that ROM, okay, it's generating samples, predetermined samples for whatever the waveform is. It doesn't have to be a sine wave. It can generate any arbitrary waveforms depending on what you've programmed in that ROM. And as it's generating those, you feed those into a digital analog converter and then filter it to get it back to an analog waveform. So whatever pattern you program in the ROM, you can generate it at different frequencies depending on what your clock is. So that's how, and most of the frequency synthesizers that work that way are, a lot of times they call them arbitrary frequency generators, because you can have different patterns. So you can generate square wave, triangle wave, sine waves. You could even plug in your own custom ed wave. So which of the following is characteristic of a direct digital synthesizer, or DDS? Let's see. Yeah, okay. The basic thing here is there's the two types, the direct digital and the phase lock loop synthesizer. And we just talked about the direct digital synthesizer with the accumulator and the lookup table. So what type of frequency synthesizer circuit uses a phase accumulator, lookup table, D to A converter, and low pass anti-alias filter? What could that be?
DDS.
What information is contained in the lookup table of a direct digital synthesizer?
Bravo.
Just the amplitudes for each sample. In other words, you could actually reproduce a waveform if you ran it through an A to D and captured all those samples and put it in that prom. You could totally reproduce whatever that was if you had some reason to do that. The other type is a phase lock loop, where you make use of a phase detector, which is a little circuit where it can detect the difference in phase between two signals. I think they do it by looking at zero crossover, where they don't cross over at the same point. A low pass filter, a voltage controlled oscillator, a VCO, because you have to vary the frequency with an analog input, which is the error signal that you get from the phase detector. And then a reference oscillator. It's typically used to just do frequency synthesis. You can use it as a type of FM demodulator as opposed to a discriminator. You can demodulate FM. I suspect you can do PM. You can even do AM. In fact, one of the modes this one does is SAM. What does it stand for now? Anyway, you use the phase lock loop to do the demodulation, and can actually, the error signal it generates is the frequency offset. So you can actually use it. We use it here to calibrate it, because you can calibrate the frequency by adjusting that offset to zero and get it accurate to within a fraction of a hertz.
Very accurate oscillator.
Yeah, temperature controlled crystal oscillator. Okay, the phase lock loop. I think I was getting ahead of myself before talking about the two dividers, but so you have a reference oscillator and you run it into a frequency divider that you can change the amount of division and feed that into the phase comparator along with the output of the VCO, which can be divided into the phase comparator. So when the output of the phase comparator essentially is at zero, and you filter out all the high frequency stuff, so you just integrate that, and you use that as the error signal to drive the VCO. So at the point where the VCO matches this frequency range determined by the ratio of these two things, then it's essentially going to be locked in phase at that frequency. As if the frequency's off, you're going to get an error signal, which is going to drive it back whichever way in order to get it back to that point where the phases compare. So it's not really locking the frequency, it locks the phase, not only the frequency, but the phase. So you can have a frequency generator that is the right frequency, but it could have phase shift in it. Not with that when it's locked. Um, for Apollo, the receivers for the telemetry were phase locked and would actually lock on the frequency. What is a phase lock loop?
Holly.
Which of these functions can be performed by a phase lock loop? Yeah, I think it's hard to do the others.
Bravo.
Oh, that was Sam was synchronous AM modulation.
I like to know how you use C.
With a phase lock loop?
Yes.
I'm sure somebody could take your money and say they'd do it. Okay, so one of the problems is spectral purity on these things. Even in the case of a phase lock loop, you have a thing called phase noise. So it's kind of like phase jitter. It's one of the issues. In the case of the with the dividers in there and on the direct digital, you can get a lot of spurious signals because you're really dealing with digital waveforms in there. So you've got a lot of square waves running around. This is one of the things, there's a thing I found about how they measure the goodness of a direct digital synthesizer by looking at all these spurs compared to the output frequency and, how far down they are. So they call that the spurious free dynamic range. So what are the major spectral impurity components of a direct digital synthesizer?
Charlie.
Okay, a high accuracy oscillator. One of the main ones is called a GDO or GPO, GPS, excuse me, disciplined oscillator, where you lock, it's kind of like a phase lock, and you lock it to a GPS signal so that it's going to be accurate to what is it, trillionth or whatever of a cycle.
It's crazy.
Yeah, whatever the cesium clock is. And then, of course, you can have your own rubidium stabilized reference oscillator in the laboratory, maybe. Or you can use a temperature controlled high dielectric resonator, which is one of those ceramic ones that Chuck was talking about, or a TCXO, a temperature controlled crystal oscillator. And you get those in very small surface mount packages now for like 10 or 12 bucks. Mm-hmm. Yeah. I don't know exactly what's in it, but it's supposed to be a temperature controlled crystal oscillator. The one I'm using is 25 megahertz, and it's accurate to much, much less than a part per million. So which of the following is a technique for providing highly accurate and stable oscillators needed for microwave transmission and reception? Now, these things are more important at microwave because of the high frequency, and 1 part per million at a gigahertz is a lot of cycles. You don't care so much about HF.
It's our famous delta.
I didn't hear that.
It's our famous delta for the answer. All of those.
Yep, it's all of them. Okay, so that's it. we learned about three kinds of oscillators and drift and synthesizers and phase lock loops and TCXOs and GDOs and all that good stuff. Sorry it took so long. I can't entirely blame it on the power